Salam and welcome everyone. So today we're going to be working on the question on the screen that says the standard molar entropy of liquid water at 273.15 Kelvin is 65 joule per mole Kelvin, and that of ice at the same temperature is 43 joule per mole Kelvin. Calculate the change in molar Calculate the change in chemical potential of liquid water and of ice when the temperature is increased by 1 Kelvin from the normal melting point. Given your reasons, explain which phase is more thermodynamically stable at the new temperature. So we were told that 273.15 Kelvin is the mean temperature, and we're told that molar entropy of liquid water at that temperature is 65 joule per mole Kelvin, as well as the same temperature, the molar entropy of ice is 43 joule per mole Kelvin. So I'm just going to write that down. So the temperature is 273.15 Kelvin, okay, and the molar entropy of water is 65 joule per mole Kelvin. And that of ice, the molar entropy of ice is 43 joule per mole Kelvin. So the change in temperature is just simply going to be the T final minus the T initial. We're told that the temperature is increased by, because they said by, we're not gonna think much about it because they've just really told us what the change in temperature is, which is just 1 Kelvin. Because it was increased, we're going to have plus 1 Kelvin. So it's the increase is positive. So that's just 1 Kelvin. So these are the parameters you need. And yeah, these are the parameters you need. So when they've given us all of this information, we're told to calculate the change in chemical potential. So that will be the change in chemical potential, delta meaning change. And then, of course, the mu sign is the symbol for chemical potential. So we're asked to find the change in chemical potential of liquid water and of ice. So we're going to be calculating two, and given your reasons, explain which phase is more thermodynamically stable at the new temperature. So of course, you're also expecting that at the end, we are going to compare two results. So it's important for you to know now that the formula we're supposed to use for the change in chemical potential is negative the standard molar entropy times the change in temperature. So for water, let's start with water. For water, that is going to be change in chemical potential of water is just going to be negative, okay? The molar entropy for water. So which one is it for water? We have 65 joule per mole Kelvin. So negative 65, oof, 65 joule per mole Kelvin times the change in temperature, which is just 1 Kelvin. So you cancel out the Kelvin, and a change in chemical potential of water is just simply negative 65 times 1 would just be negative 65 joule per mole. And then the one for ice is change in chemical potential of ice is negative. So the molar entropy for ice is just 43 joule per mole Kelvin. So negative 43 joule per mole Kelvin times the change in temperature, which is just simply 1 Kelvin. So that would be 1 Kelvin. So the change in chemical potential of ice becomes negative 43 joule per mole. So this is basically the answer. So we have successfully calculated what we're asked to calculate, what is the change in chemical potential for liquid water and of ice. Now we're asked to determine which phase is more thermodynamically stable at the new temperature. Now, the important thing you have to know, the general law, anytime you want to find the more thermodynamically stable phase, is for you to note that when you're dealing with chemical potential, the lower the chemical potential, the more thermodynamically stable the phase is. So to answer your question, generally, the lower the change in chemical potential, the more thermodynamically stable the phase is. So that's like the general rule. So now we're told which one. They said giving a reason, explain which phase is more thermodynamically stable at the new temperature. So when the temperature increased by 1 Kelvin, you see that the lower chemical potential is out of water. So you cannot write the more thermodynamically stable phase is the water phase, the liquid phase, because it has a lower chemical potential of negative 65 joule per mole than of ice, which is negative 43 joule per mole. So I can write that now. So the more thermodynamically stable phase, the more the thermodynamically stable phase is the water liquid phase, because it has a lower chemical potential of negative 65 joule per mole in comparison to the chemical potential of ice at negative 43 joule per mole. So this is basically how you answer a question like this. I know you guys are used to seeing me only doing calculation problems from the physical chemistry thermodynamics textbook, the Atkins Physical Chemistry Thermodynamics textbook, the 11th edition, for those of you who are new to this video or new to my series. So I just wanted to say that this is just, a question where you have to be able to do calculations and you have to give a result of your calculation in words. Like you have to compare and contrast two different um, experiences, two different processes, not experiences, two different processes for you to be able to determine which is more favorable. I have done a similar question for the B part of the question on my channel. So make sure you look at the description box and try to attempt this question on the screen. So now we are at the end of the video. If you're a student who is struggling in any of your STEM related courses, whether you're in middle school, high school, or college, make sure you email me at shahabitutoring@gmail.com. I help students succeed in all your STEM related courses in middle school, high school, and college. I also help in mentoring students who may be struggling in their academic life. So if you know that you would like a tutor and a mentor for your academic life, make sure you email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.